Swayam Prabha. Digital India. Educated India.
Professor Jim Libby is a prominent professor of physics at the Indian Institute of Technology, Madras. He is an experimental particle physicist who has been a faculty member at the institute since 2009. He specializes in experimental high-energy particle physics, flavor physics, CP violation phenomena, precision measurements, and silicon detectors. He heavily collaborates with international accelerator laboratories working on prestigious global experiments including Bell 2 from Japan, BES-3 from China, and the CMS experiment at CERN in Switzerland. His work primarily revolves around studying the weak interaction between quarks, matter-antimatter asymmetry, and exploring new physics beyond the standard model. He is also noted for utilizing machine learning tools for complex data classification in precision electron-positron collisions. He received his undergraduate and postgraduate degrees from the University of Oxford, finishing his PhD work in 1999, primarily based at CERN in Geneva. Before joining the faculty at IIT Madras, he worked as a postdoctoral researcher at the Stanford Linear Accelerator Center and held research positions at Cornell University and Oxford. At IITM Department of Physics, he acts as a principal investigator for core particle physics initiatives. He is widely appreciated by students for his charismatic and witty style of lecturing on nuclear and particle physics. Can we all welcome him?
Thank you very much. Okay, that was quite the trip down memory lane. Thank you very much. So I'll give you two lectures, one today and one tomorrow, slightly different topics. So today I'm going to introduce the theory of relativity, or more specifically, the theory of special relativity. So first of all, I just wanted to know, what do you know about relativity? Just anything you know at all? Any equations, perhaps? Yeah? Yeah. So for relativity, speed of light is a constant. And I'll come back to that. That's the key part of special relativity. Anything else? You're busily discussing there at the back. Have you got an idea? Purple shirt there. Anything about relativity you know? No? Okay, good, because you will learn more in the next 50 minutes. So, aside from this, usually the thing what people say is Einstein, right? And certainly he was instrumental in this. And the other thing is E equal mc squared, right? Now that's harder for me to get to in 1 hour, but I'll give you some idea of where that comes from by the end, okay? But what is certainly true of relativity is actually it's not true modern physics. It's a very old concept, okay? So to start with, let's start with what's called Galilean relativity. So this is 16th century, okay? Galileo stated something that's very close actually to the final version of relativity. He just said, the laws of mechanics are the same in all inertial frames. So this statement relies also on understanding what an inertial frame is, okay? And all that is, so this pen is not so good. I'll try another. better. Moving at constant velocity. To another, okay? So this is just born out of experience. People realized that if you were moving on a ship, moving at constant speed, nothing was different about how mechanics behave. If you gave something a push, it would continue to move until some force slowed it down, right? And it would move in a straight line and all of these things. So everything was the same. So it was born out of experience, and there was nothing to suggest that this was violated in any way for a long, long time. And it's important that we just look at this mathematically for a moment, and we'll write down what a Galilean transformation is. I assume you've probably seen this. And this kind of notation is important for everything that we'll discuss today. So I look at my coordinate system, which I will call this one without any primes on S. And then I'll have another one moving with some velocity, which will always be in our common x-axis. And this we'll call S prime. And then I can relate together the coordinates in the two. Okay? So x prime is just x minus, so this is a modulus of this velocity, I'll call it v times time. And then the other coordinates, and z you can't see, but it's unchanged also. And it's the last one that's very important. Okay? Here, we're saying time is absolute. Okay, no one thought that there was any difference between a clock that was moving and a clock that was stationary. And this is the idea that we have to give up, that there's any universal idea of time. Okay? So these formulae I'll come back to because they're very useful in understanding why no one noticed this before. Okay? And I assume you've solved various problems of relative velocity, so you figure out when one thing is moving relative to another, you can work out the net velocity between them. And this is all related back to this Galilean transformation. Okay? So this is an assumption. Okay? So that's the first part of this, where we just discussed what relativity was for a long time, okay? But before I move to the special theory, I just want to talk about invariance, which is a very important concept in a lot of physics at a higher level. And you are familiar with this, but you probably haven't thought so much about it, okay? So in physics, we basically use two types of objects to describe physical things, okay? It's not entirely true, but I don't want to go into phenomena. And these I refer to as scalars, which are just numbers. So this is something like energy, temperature, the magnitude of some quantity, a speed, whatever you want, okay? So these are just numbers. Do they depend on the frame in which you measure them? No, they cannot, right? It's us who always imposes the coordinate system. Okay? And then we have vectors. which is the ones that you've got used to in mechanics. So these are things like momentum, and maybe you've looked at magnetic fields as well. These are objects which have some directionality associated with them. Now, this is slightly trickier to think about why these are frame independent, okay? Because you know, right, if I have some vector, I can use my other colors.
So both scalars and vectors are frame independent.
Have to be. No. Okay, they've got to have suitable transformation properties, okay? And I'll explain what those transformation properties are in a moment. Scalars are easy, right? That's an absolute magnitude of something. You can't have more energy just by changing how you look at the system. That you can understand, and the temperature won't change and so on and so forth. Vectors, as I'll explain, a little more subtle, but it's very important for how we look at relativity. So what I'm saying is the physics is invariant, okay? Not necessarily how we define the object. So these two vectors will be the same. If I were to throw my pen at you, if I got very angry in my lecture for some reason, that will move in a straight line and it will have a direction. And depending on whether you're looking at it or you looking at it, you'd look at it and you'd define the vector in a slightly different way, probably, because you would think I'm the origin and whatever. You'd find that the vector is invariant if you translate your coordinates. But it's also invariant if you rotate your coordinates, okay? So, you know, I would traditionally define a nice pair of Cartesian coordinates such that the vector is in the plane of the xy coordinates. And I would give this vector two components, vx and vy. Okay? But, and this would be my S in this case. But someone may like to do things on a slant. They might be listing in some way. So they will say, no, the coordinates are like so. Okay? This is x prime, and this is y prime, and this is my s prime. Okay? Now v will be different, right? This will be some vx prime and vy prime. And they will have different values. You can see this and you can do the geometry, and what it will depend on, and you probably have seen this at some point, should be black. It will depend on this angle at which you've rotated things, and the coordinates will change. They'll become a mixture of the original coordinates, vx and vy. So vx and vy essentially become, sorry, my pen's right, vx prime becomes a function of vx and vy and theta. Okay? I won't write all this out because I'll come to something more interesting later on. Okay, so this is what they are, and that's how you transform between the two coordinates. So they're not the same, but something is the same in both of these cases, and that's their length. So vx squared plus vy squared will be equal to vx prime squared plus vy prime squared. Okay? So when you think about a physical phenomenon like a momentum, that's good. The magnitude of the momentum remains the same. That's the actual physical thing that will require a certain force, which will have to be the same in the two frames, and so on and so forth. And so the physics looks the same, okay? And you can show that classical mechanics is completely indifferent to how you define your coordinate system in terms of a rotation. It's completely rotationally invariant. Of course, we choose coordinates that make our lives easiest. So, like here, I chose everything in the plane, but I could have chosen a coordinate system such that the z-axis wasn't pointing out of the board, and I have a much more complicated system. But a series of 3 rotations will always get me back to the original coordinate system, and everything will be invariant under this. Okay? So this invariant quantity, essentially it's saying, because I can take the square root of this, lengths remain the same. And this is actually the technical definition of a vector. A vector is defined by its transformational properties. I say anything that's a true vector will have its length unchanged as I move between coordinate systems. You can easily think of the components of a vector not depending on, say, x and y linearly, and then that wouldn't be a vector anymore. So if I had something like x squared plus y squared as the first component and something else, that wouldn't be a proper vector. And it's actually, this whole language goes to higher dimensions as well. So when I was saying we have scalars and vectors, there's actually a whole class of objects called tensors, which we describe physics in, because they're invariant under rotations. Okay? So what has this got to do with relativity? I'll come to a little bit later. So we have two things. We have Galilean relativity, and we have this invariance. Now you would ask yourself, why do we need special relativity? What was the motivation that was there for Einstein to move away from this idea that time was an absolute, and why we had to do something far more complicated? So the need for relativity. So often this is introduced with the idea that Einstein was on a train and was thinking about someone on the platform and how they might see things differently to him. And that's not true, okay? The thing that really mattered was in the middle of the 19th century, James Clerk Maxwell suddenly united three different aspects of physics. He united electrostatic phenomena, magnetic phenomena, and optics, all into his theory of electromagnetism. So have you studied electromagnetism a little? Things like Gauss' law, Faraday law, Lenz law, these kind of things, or not yet? Okay. But what you learn is that electric fields and magnetic fields are related together by something like Faraday's law, where you can generate a current by changing the flux. And this unified theory was incredibly important. So it all comes from electromagnetism, as it's called. So this is the unity of electric, magnetic, and optical phenomena. Okay? And one of the important consequences of Maxwell's unification of the electromagnetic phenomena was the fact that he predicted electromagnetic waves. Okay? So electromagnetic waves, if you write down his equations for electromagnetism, so-called Maxwell's equations, you get something called a wave equation out of this, which is just like a traveling wave, but now it's not a physical thing that's moving, it's a field. Or a field is a physical thing, but something that isn't really a visible, intuitive thing. So what you have in an electromagnetic wave, I should draw this on the next board, I think. So again, I have a coordinate system. Here I'm going to have Z. And this, if I draw, so the red here is a magnetic field, and the blue is an electric field. And you have these perpendicular waves that are coupled together. Okay, so it's a combination of the two. But what you have is a wave traveling in this direction. So you'll have its speed in this direction. And what's remarkable about Maxwell's theory is that the equation that you solve, the so-called wave equation, will always have the same speed, irrespective of whether I'm in S or S prime. Okay? So, EM theory that this wave, the EM wave, has a speed c, irrespective of whether the frame is moving. You know, if I solve these equations in S or I solve these equations in S prime, I get the same speed. Okay? So this is something that's not well understood about relativity, is that the answer was already there. Electromagnetic theory is a relativistic theory. It's just people hadn't interpreted it correctly because they were so worried about the absolute nature of time, because they thought time had to be the same everywhere. Okay? So this was fine-ish. Okay? So people now needed to reconcile this with how they thought the universe might work. And what they said was that, well, we know if we look at waves on a lake, they're traveling in a medium. Or if I'm listening to sound, I know that's the air that's vibrating. So perhaps there's something, you know, the vacuum isn't really the vacuum. The vacuum doesn't mean nothing. There's a big amount of matter that we don't sense, which has got the waves propagating in them. So what they predicted, to make sense of all of this, is these waves move in a substance, but we can't see it, we can't feel it, only the waves are feeling it, all right? This is already dodgy science, right? When you're postulating things you can't see, you know you're normally in trouble, okay? So this is what they wanted, and this is the theory that prevailed. And people said, okay, there will be this ether, and this will have the waves, and so on and so forth. Yep.
In an electromagnetic wave, the electric field, magnetic field, and the velocity are perpendicular to each other.
Yes.
So then, in that case, shouldn't the velocity be in the y direction?
So it depends how, so I've drawn X and Y. You had a choice, it doesn't have to be. So I've put the magnetic and electric fields in the X and Y directions, and then that means that it's always perpendicular. So some people will draw it in the, you just rotate your axis around. It's just a convention. So what people thought was if there's so this is the sun, and we have the Earth going round. This would be full of ether, okay? And so as the Earth moves, because it's got quite a large speed, some thousands of kilometers per hour, there would be a direction with the Earth, we call it V, and there'd be, so this, and then there'd be a direction perpendicular to it towards the sun, okay? Sun's orbit, it should technically elliptical, but it's almost circular, right? So to with first order, you'd look at these two directions. And two Americans in the 1890s, this 1897, Michelson and Morley, built an interferometer. Have you any understanding of interferometry, wave phenomena, constructive and destructive interference? Yeah? So if waves have a different path, if you bring them back together, sometimes they enhance one another and sometimes they cancel each other out. Constructive, destructive interference. So what they did was, so this would be like this is glass. I'll draw it and then label everything in a moment. Then you have a light source. How am I doing for time? Okay, go a bit faster. So this 45-degree glass plane, some of the light's transmitted, some of the light's reflected off it. So this splits the beam. Some goes this way, and some goes this way. And then it gets reflected back. Maybe I should draw a different color for this one. Clear. So it gets reflected back, and carries on down here. And the other one goes this way, and comes back. Okay, they're obviously overlapping, but I want to draw it as such, and then they'll come together down here. So here you have a detector. They just looked at the light. And what you see are dark and light patches where the light's traveled enough distance to interfere and not interfere with one another. And what they did was they aligned one of these in the direction of the, I'll do it the other way around. It's like this then. This one would be in the direction against V, say, the motion of the Earth. And this would be perpendicular. And then they thought, okay, now our usual Galilean relativity must apply. There's going to be a slightly faster light wave, or slightly slower when it's going this way, slightly faster this way. And this way, it won't be that affected very much, but it has to travel a little bit further because the mirror's moved. Okay? So you do the geometry of this. My notes. And sorry, this question? Oh no. So this T parallel, wrong pen. T parallel you can show that this becomes this time to go this way in blue, and then so excuse me, ma'am, it's a little distracting if you. And then T perpendicular, that just comes from the mirror moving. And this is 2 times the length, 1 over. So I'm not going to have time to go through proving this, but it's a little bit of geometry in both cases, just adding a bit of velocity, taking away a little bit of velocity in the 2 legs here. And this one is just the mirror moving a little bit by v, whatever time it takes. And you end up with this expression. Now, I don't know, have you done Taylor series? Sorry, question. Yeah, so sorry, I've mislabeled that. Thank you. And this is the parallel one, sorry. I got the wrong way around. So Taylor series, small approximations. So the velocity of the Earth is very much less than 3 times 10 to the 8 meters per second. So this is a very small number. So you can do the Taylor series here and you bring it up. So this would become essentially 1 plus. Okay. And you then take the difference of these two. and you are at a half b squared over c squared. C cubed, sorry. And there's an L here, yeah? So, yeah, that's right, LV squared. So this is what you end up with the difference. And what Michelson-Morley measured for this difference is equal to 0. That's the measurement. And this was repeated many times, more precise apparatus, different people did it, everyone got 0. Didn't matter which way your light went, it didn't look like there was any difference between the paths. The interference pattern looked as if there was no difference either side, and they got ever more accurate. They did this over several years. And people came up with some ways the ether was changing with the motion and this and that. But it took something entirely different from Einstein to actually solve the problem. Okay, so that's Michelson-Morley. Yeah.
So what is
L here is just the distance, sorry, between the light goes here. Yeah.
And so what is V here?
Sorry, which?
Down below.
Detector. So this would be, so when you do interferometry, you get fringes of light. You may have seen this. If you put a slit and you get the light to come through, you'll get the constructive and destructive interference, single slit. So this is exactly the same thing that you would see. You would see, depending on how slight changes in the distance across the reflection on this thing will lead to different path lengths and different amounts of interference, okay? It doesn't exist, so don't worry about it. It's a medium in which the light travels, right? So it was thought to be something related to electromagnetism, which was just for the waves to propagate in. So it was, it's called the ether, which is now a synonym for something that doesn't really exist. Okay, so Einstein, finally. Yeah, I'll erase here. I can see most people have been using slides or they have a very good cleaner. So this is so Einstein. (1905). He decided that Galileo and Maxwell were right. Okay? So all he said for his theory of relativity, there are just two parts to it. He says the laws of physics are the same in all inertial frames. So there's only one change here from Galileo. It's mechanics to physics. And that's just a consequence of history that they had more physics and mechanics by the 19th century. They had electromagnetism, they had optics, they had statistical physics, thermodynamics, and things like this, which weren't there. So he just says the same as Galileo, physics doesn't care which inertial frame you're in. And then he said that what you told me at the beginning, speed of light is constant in all frames. So, i.e., EM theory is correct. So really, these are said to be the two postulates of relativity, but they're actually just one. He said that this first one, if you include electromagnetism in that, means that you already get the waves moving at the speed of light, because the formulae in the theory of electromagnetism are completely invariant depending on the frame that you move in, once you've got relativistic transformations. Okay? So what does this really mean? And why where do the more unusual aspects of relativity come from because of this decision? So this statement is equivalent of saying we don't need the ether. Okay? It was saying throw out the ether, electromagnetism's correct. In every frame, the speed of light's the same. It can't sense moving through the ether at all because it doesn't exist. And we'll work from there. Okay? So we go back to our two frames. And at some t0, they completely overlap with one another. I can't draw very well. But they have the same origin at some time. And, you know, this will be our x, y, and x. And this will be x prime and y prime. And you synchronize your clocks in the two frames. So you have a clock in this frame. Okay, this is a clock. Then you also have a clock here. And they both tell the same time when they overlap with one another. Okay? But this one's moving with our speed v relative to the other one, the blue one. So at some time later, the frame will be over here. Okay, this will be our y prime, x prime. Now, at the same time we synchronized the clocks, we gave a little flash of light. Okay? And so the flash of light told us the clocks were aligned with one another, and then we let them move, let the frame move off, and we can then look at that little bit of light sometime later. So I haven't drawn this tremendously well, but essentially what that means is it will have moved a distance r in the original frame and come to some point here. But in the moving frame, that looks a bit different, but it will be at the same point. Okay, so this will be r prime, and it will have moved to that point. Okay? Now, light is an inertial frame moving in a straight line. So you know what the distance is, yeah? It's just x squared plus y squared all square rooted in both frames, okay? So I'm gonna have wrong frame, that's y prime. That's going to be the distance. And then I have okay. So we have these two distances, yeah? But we also now say we have two times. All right? We've said the speed of light is constant, but this distance, if it's being traced by this light wave, which is moving at c here and c here, that's going to be equal to c times the time in s prime. This is my s prime here. And this is going to be c times the time measured on my clock here in black.
So just for clarification, the first one, the black clock is not counted.
It's moving with respect to, the two frames are moving with respect to one another. Obviously, if I'm in S prime, S is moving. Yeah? So this is relativity. You can never say who's at rest and who isn't at rest anymore. Okay? It's just within your frame what is at rest and what isn't. So both clocks are at rest, but they're in different frames, yeah? So I have that this distance I can measure with the spatial coordinates in the two frames, but now I say there's a different time associated with the two frames, okay? So time is no longer absolute. Now, I can re-express this. I'm saying that this is equal to this. So if I subtract, I actually square it and then I subtract from both sides or vice versa. I can make these equivalent to one another. And essentially what follows is that I say okay. So what I have is that this difference is both equal to 0 in this given example. And so I just equate them to one another. And what my relationship between the coordinates must give me is this relation. Yeah. So this is the basic relation in relativity. So Einstein made these two assumptions, realized that this is what would happen in a thought experiment with light, and hence you end up with this kind of quantity, which is the difference between a time, it's multiplied by the speed of light, dimensionally this all makes sense, they're both lengths, and then that must be the same in the two frames, okay? And what this means is you must have now a different relationship than the Galilean relativity between at least the x coordinate and time. Okay? So and in the simplest version of what it might be, this is a constant to be determined. And then t prime okay. So a couple of things about this. One is I'm missing a step. Otherwise I'd fill up the whole boards again with some algebra. Essentially I could put a C and a D in front of these terms. You have to do a little more work, but you could show that they have this form, okay? Quite quickly. The other thing is, I'm assuming the transformation is linear. Anyone have some sense of why I'm assuming it has to be linear? So what I mean by linear is no x squared or t squared in here. Sorry? Who spoke? A component of a vector, that's one way of looking at it. But essentially being part of a vector, it meant it had some direction, right? And if it was, say, a momentum or a velocity, that would be a straight line, independent of the two frames. So yeah? Exactly, yeah. So you start getting curved trajectories. So this goes against our experience that we just said that mechanics is the same in both frames, and that means things would start looking as if there were pseudo forces and it'd be accelerating frames of reference. That's general relativity and something entirely different. So I'm allowed to make this assumption that they're linear, okay? And now, I missed a dimensionality thing, that's the c there. So I keep multiplying time by the speed of light just to make sure it has dimensions of length. So everything's dimensionally okay. So these are dimensionless constants to be determined. And I just plug those into this relationship up here, okay? So I just say that CT all squared minus essentially x prime squared minus y prime squared minus z prime squared. Okay, these are unchanged. Okay, maybe I should make this clear. There's no change in those coordinates that are not in the direction of the motion. Okay? And then I do the same for okay, so these will cancel out. And then I just put in on this side my whatever I. So I'm going to have b squared minus x squared minus 2x t squared is going to be equal to c t squared minus x. Okay, so there are a couple of things to note from this. I have this term which is the product of space and time, x and t. That is not going to feature anywhere in our actual relations, right? I need there's no cross term, right, in this relationship. So that immediately tells me that a squared is equal to b squared. Yeah? That's the way it will cancel out. These have opposite signs, minus sign here. So as long as a squared is equal to b squared, it all disappears. And then that means I can factorize the terms. And on this side, it just becomes a squared 1 minus b squared c squared. And that will be equal to this. Okay? So what we need is for this to be equal to 1. And then this holds true. Yeah? So this tells me and in special relativity, we call this the gamma factor. Okay, I'm running out of time. I have a few more things to say about relativity, but as I speak tomorrow, and relativity is the playground of particle physics, which is what I'll talk about afterwards, I can conclude tomorrow and then carry on with the particle physics. But the one thing I want to just leave today before I conclude tomorrow is looking at this expression when v is very much less than the speed of light, gamma is approximately 1. Okay? So we just look at this first expression. If a is equal to 1, we're back to Galilean relativity, right? Just as we'd expect. So it's no wonder we haven't seen anything because we're not moving at speeds close to the speed of light. Similarly, in this expression, okay, this is 1, but this v over c ratio here, that's going to tend towards 0 when v is very small. So this term disappears, so you have time is absolute. So Galileo wasn't wrong, he was just working at low speeds. Okay, so relativity reduces to what we'd expect at low speeds. Okay? So I have a couple more things that I want to talk about tomorrow. One is the full Lorentz transformation, which you can derive from this. And then something called, there's some consequences, time dilation, and then a little bit on length contraction simultaneity, and then I can move on to particle physics. Okay? So I will continue this lecture a little bit tomorrow and then talk about particle physics for 45 minutes. Okay, I can take any other questions, but I should finish by 10 o'clock. I think. Yep.
We should actually talk about the matter and
Yeah, I can. I will mention what antiparticles are. I can't give you any great insights. That's why we still study it. Okay? It's a mystery. The mystery of the universe is why we live in a matter-dominated universe. Okay? Oh, the antimatter disappeared. Sorry? Ah, okay. When matter and antimatter come together, they annihilate with one another, as you may know from science fiction books and thrillers, etc. Things go bang. So when there was the rate at which it annihilated was out of balance, out of equilibrium. So there was more matter than antimatter. So it no longer, not all the matter disappeared, okay, before the antimatter. So there was an asymmetry developed. These are things called the Sakharov conditions. You need some mechanism to generate that imbalance, and it has to be out of equilibrium. And also baryon number must be violated. But that's a different story, more protons than antiprotons. But these conditions have to be there to get that asymmetry. So this much, we know what happened. These things happen. It's why they happen we don't understand. We have some idea. I can generate it in the lab, but in a very small amount. Not enough to explain where all the structure comes from. So this is more a question for tomorrow. But this is quite, I'll say a bit about this. Okay. Anything else about relativity? Okay. Yeah, to do time dilation. And then time dilation is very much related to particle physics, so I will talk a bit about that. And also I need E equal mc squared as well for particle physics. So I'll get to those two things. It won't take 10 minutes, and then I'll talk something about particle physics. Okay. So I stop here. I don't quite know what the format is. I was told 50 minutes, so okay. And I saw another lecturer at the back of the room at one point, I think. So I'm done for today.
On behalf of all the students here at RSIC, I would like to extend my thank you to Professor Jim Libby for his inspiring and intriguing lecture on special relativity. We all truly enjoyed it, and it was food for the thought. Thank you, sir.
All right.